Welcome to 6G RF Frontiers. In this series, we'll explore how radio design is evolving beyond 5G into terahertz frequencies, sensing-aware systems, and an AI-driven optimization. Today, we'll look at where 5G RF reached its limits and what's pushing us toward a completely new RF frontier. 5G pushed RF technology further than ever. Massive MIMO, beamforming, and then mmWave systems up to 52 GHz. But these advances came with trade-offs: lower efficiency, higher complexity, and serious thermal challenges. Integration limits in packaging and the interconnects showed us that simply scaling 5G isn't enough. Power amplifier efficiency drops fast as we demand more linearity, digital distortion, and beam calibration at cost and latency. Dense arrays overheat, and every bond wire or VIA vertical interconnect access becomes part of the RF path. These are the walls we have hit with 5G hardware, and they define why 6G must rethink the RF chain. 6G targets terabit per second speeds and then microsecond level latency, plus new features like integrated sensing and communication. Achieving that means moving into the sub-THz range, roughly 90 to 300 GHz. At these frequencies, propagation, materials, and even test methods change completely. When you move about 100 GHz, since getting serious, RF design becomes much more difficult. First problem: free space path loss. Compared to 28 GHz, you lose about 20 dB more power over the same distance. That's a big jump. Second problem: the atmosphere. Oxygen, water vapor, they actually absorb the signal. So you don't have a wide, clean band to use. You only get small usable windows. And the result? Ultra narrow beams, very precise alignment, and antennas with extremely high gain. At these frequencies, you are not just designing a radio anymore, you are fighting physics. 6G wouldn't rely on a single base station box anymore. We're moving towards a distributed network of intelligent surfaces and sensing nodes. Reconfigurable intelligent surfaces will dynamically shape beams. Integrate sensing and communication will let the same hardware sense its environment while sending data. These new architectures require extreme phase accuracy and very wide band front ends. At sub-THz, even short PCB tracers behave like waveguard. Designers are tuning on gainer on side C, I on P, and then side G by CMOS to reach the needed gain and power. Antenna in package and then 3D integration merge RF, antenna, and then digital logic into a single structure. It's a shift from component level design to full stack co-design. Power density is now the main limit. In many cases, heat becomes the problem before the device even reaches breakdown. So the real challenge is not bandwidth anymore, it's efficiency. For 6G hardware, efficiency will matter more than bandwidth. And today, cooling and material science are just as important as RF design. They are sit on the same engineer's bench. The role of the RF engineer is expanding. We need cross-domain knowledge, RF, AI, and photonics working together. Collaboration and optimization will rely on digital twins and machine learning loops rather than manual tuning. Our challenge is to learn how to train radios instead of just tuning them. In the next episode, we'll explore the sub-THz spectrum in depth, propagation limits, absorption peaks, and what that means for real link budgets. Subscribe and follow the channel if you are ready to go beyond 5G. This is 6G RF frontier. Thanks for watching.